Okay, thanks for the introduction. We're going to cover today securing data pipelines at the storage layer. I'll give a bit of an introduction to Superna, what problem we solve, and how this relates to AI and machine learning with Trino. So a little bit of background on Superna. So we are a company that's been around for 15 plus years, 3,600 customers globally, 5 exabytes, or at least maybe 6 by now, globally. We have been focused on unstructured data storage and security solutions for a number of years. And I'll walk through some of the key challenges and how we address the new paradigm of joining structured and unstructured data with solutions like Trino. So session summary. So we specialize in file and object data repositories. Those are commonly used in a Trino environment as a place to store structured data using various data connectors, and of course, connecting into existing structured data sources like SQL databases and so on. So we'll look at specifically AI ML pipelines as it relates to the use case for Trino, which can be used in many analytics scenarios. And we'll look at some new technology that we're introducing that's going to help secure the SQL layer, but more importantly, secure all the data in your data pipeline. So I'm going to use the term cyber storage. Cyber storage is a category that was created by Gartner about 2 years ago. And it's essentially applying security at the storage layer and gives you active defense, or the ability to monitor user behavior, anything that's impacting your data and looking at what's happening. But more importantly, it's about prevention. So it's early detection, seeing dangerous behavior around your data structures, and taking proactive or offensive security and taking action against a machine or a user. So what do I mean by offensive security? This could include blocking access to the storage. It could be creating snapshots, which are a common feature of storage systems, and include all the options and capabilities to not only identify a risk, neutralize the risk, but help recover the data. This is broadly defined as cyber storage. It is predominantly focused on file systems and object S3 platforms, and we're taking that to the next level and including SQL, and that's what we're going to talk about here. We're also going to go through a short demo. So if we look at traditional security architectures, we boil it down to, you've got network security, firewalls, IDS, IPS systems, you've got application layer security, and then the data itself. So storage devices, file systems, object systems. It could also be relational databases. The data layer has largely been overlooked as a layer that can add value in securing the end-to-end stack. So we'll call this cyber storage. And as you can see, as a layered approach, you definitely need the network. You need application level security that can include endpoint protection. But now we're going to add a new layer. And this is the area that Superna specializes. And we've been focused on this layer of security for almost 15 years. And we like to give this handle: prevention is the new recovery. If you can detect an anomaly, prevent an attack, and mitigate the damage to your data, you avoid massive data recovery, and you can trust the data systems because you've got all the historical access patterns and can go back and prove that it was a limited impact or know precisely which machines or users impacted or touched your data. So data lakes and security. So if we look at one of the core values of Trino, it's the ability to connect disparate data sources and make sense of it for analytics purposes. In this use case, in this session, we're going to be talking about how it's used for data pipelines. So if you're connecting to all these different systems in an enterprise, that often uses connectors. Those connectors use privileged accounts to gain access to the data. That's one attack surface, is you're using service accounts. Another consideration is that when you use a service account, you're now representing users through the service account. And so it appears to traditional security tools like all of this data is being requested or manipulated from the service account, not from the actual user that's logged into Trino. That creates a context gap where security tools no longer have the context. So how do we address this solution? Well, if you want to enable a complete chain of custody, which is who did what when to your data, originating from that Trino session all the way through the SQL layer, all the way down to your file and object, you need a new approach to securing your data lake. This is precisely what Superna does and what we'll show with this demonstration. We've had products in the market that can look at file system activity over SMB or NFS. We can do the same thing for S3. But if the requests are originating from Trino servers, it all looks like one user. There's no context applied. So how do we create a unified security layer that includes SQL, SMB, NFS, and the S3 protocol? Well, this is where cyber storage comes in and moving our capabilities from the file system object store levels right into Trino itself. So is this a problem? So it is, according to Gartner, with 30% of enterprises surveyed, that their AI infrastructure has had some kind of privacy breach. That's a very big number, and it's probably well underreported. So enterprises today are focusing on how they can better protect their data. They're very concerned about AI ML and the data privacy and risk concerns of data poisoning and all the different new attack surfaces that exist around AI and ML pipelines. So this is an area of concern for enterprises. And if we apply this to Trino, it's very common for Trino deployments to collect data from structured databases using connectors. It is also very common to use file systems and object stores to store relational databases and say something like Hive or all the different options that exist to create structure out of unstructured data platforms. This may also be where the data is originated before it's uploaded or ingested by Trino and then used for analytics purposes. So when looking at this, we can see that Trino is the SQL layer, and there's data coming from databases. There's existing data in, say, file systems or object stores, and that all the disk I/O is now showing up as if coming from SQL, which is actually translated to file system API calls, so SMB or NFS, or S3 in the case of an object store. So this is sort of the problem statement. And the impact of this is it creates a new attack surface, and it also can reduce the effectiveness of existing security tools because they no longer have the context of the user account or the source IP address of the user. So a bit of a recap here. So in order to secure your AI ML, you have to trust the input. The input is the training process, the ingestion process, and the various stages of machine learning. So if we think about the input, the training data is the weak link. So if I go after the training data, I have the opportunity to maliciously change the training data to affect the AI models that are produced off of that. So this is the area of the pipeline that you need to focus on first and create a zero trust concept around your training data. And that training data could originate in structured databases. It could be existing file system and object stores, but it's all coming together within Trino, where you then go through the various stages of data collection, model training, you do evaluation, tuning, customization. So as the data flows through this pipeline, at each stage, there is an attack surface that if it's flowing through Trino, we need to get the context of each of these stages and apply a zero trust concept at each and every stage. When this was a file and object only world, we had that covered. Now that we move up into the SQL layer and we're now combining structured data into this pipeline, we need a new solution. So I'm using here the Gartner TRISM model. There's several security frameworks around AI pipelines, but the one we're going to focus on is the largest attack surface. So on the left-hand side, we call this the development and deployment. On the right-hand side, the green, this would be the runtime. So your model's built, you've got prompts, you're inferencing, you're answering queries from users or doing whatever your model was designed to do. But I like to say it's garbage in, garbage out. If the attack surface has already polluted or poisoned the data that enters your model, the runtime isn't going to address that. So the Trino solution is going to sit over here on the left, where the initial steps of collecting data, tuning your models, prompt engineering. We want to ensure that everything that's occurring to the data throughout the entire pipeline is in full view of security software to identify suspicious behavior. So the logo in the middle is where we focus our attention, which is also turns out to be the largest attack surface. If we think about GPU farms and doing training, if you're training over weeks or months and all of a sudden you have a cyber incident, can you trust the output of that training session, or do you have to start over? The cost of starting over or not knowing if your data was safe during a cyber incident, the costs can run into thousands or millions, depending on how many GPUs were involved in the training process. So the risk of not securing your data pipeline isn't worth it. The cost to the business is enormous. So we have a 3-pillar architecture that sits at the data layer. One is traceability. If I don't know who did what when at any layer, regardless of the protocol, and I'll treat SQL as the protocol, SMB, NFS, or S3, then we simply can't trust the data. So you need traceability. We need to identify the user, what they did, what data they manipulated, and we need to keep that essentially forever. Anomaly detection. In these environments, in a zero trust model, we've got legitimate user access. So we need to ring fence the users and the hosts that are authorized to touch the data. We then need to enable anomaly detection so that we don't trust the trusted users and hosts. That's a foundational component of any zero trust architecture. So we need to be looking for malicious activity. Ransomware possibly is a threat, but if it is, we need to be looking for that as well. We need to look for unauthorized access. We need to look for tampering evidence. If a user's primarily searching for data and now they're doing mass table and row updates, that might be a concern that needs to be looked into. And then data exfiltration, which could include model exfiltration. This is the ability to extract the model itself and steal it at the end of the pipeline. So I need to be securing the data all the way through this process. Part of the traceability aspect of this is I need the ability to keep an immutable copy of my training data so I can go back in time and recreate any view of my training process to ensure that I can run the training process again and produce the exact same model. If I can't do that and I don't have immutable data checkpoints, then I have no ability to root cause issues in production or prove that my model was not at fault. So you need to keep immutable copies of your data throughout the entire pipeline process. So if you enable these 3 key pillars, you can address that data attack surface within the TRISM model around the data itself. So what has Superna done? Well, we have gone and adapted our AI machine learning process into a Trino environment. So how did we do that? Well, looking at this slide, you've got Trino CLI clients, SQL queries coming into the query engine. In our case, we're using DB Beaver just to mount tables, create tables. And we've written an SQL event listener using the APIs available from Trino. And its purpose is to extract the data that we need to feed our behavioral AI model that's used for SMB, NFS, and S3. In our case, we use Kafka as a message bus to feed our training process. And so what we've done is we've written an event listener and we will publish that data into Kafka topics. So what data are we getting? Well, the event listener can capture things like the source IP of the SQL query, the logged in user, the tables that were involved in the query itself, select, insert, update, delete. We also get the rows returned or the rows impacted. We get the duration of those queries. So we get a lot of metadata that can be used in our anomaly detection. All of that data is now fed into a Kafka topic where it's then consumed by our AI engine. Just a high-level view. Once the data enters Kafka, there is some data manipulation we need to do because our models need to normalize data coming in from SMB, NFS, S3, and now SQL. So we've published the data in a raw format, and then we pre-process that data inside of our Kafka topics. There's two main topics that we use. One is just the raw events, whatever was produced by the event listener. One is a processed where it does some logic to combine various fields like the user IP address, the tables, and the actions. And it aligns this over a time window and publishes that into a separate topic. Then on the right-hand side are the models themselves, and these allow us to go through and look for anomalous behavior, and that's the data collection phase that we then build our own models, and then we run live inferencing with those models. So we take a look at the big picture. So we've got Trino deployed. We've got file systems deployed, SMB and FS file systems that are storing some of this data, object stores. We can now take inputs from Trino, the event listener. We can take inputs from the auditing capabilities of the storage. That's a common feature of all file systems. They can audit user activity. And typically for an S3 object store, it's usually the web access log, but it contains essentially the same information, the user, the get, the put, the object. And all of that information goes in to our Kafka topics. And then we pre-process that data, create the training data set, build our AI cyber storage models that now include SQL as one of those protocols that we can now support. And then we can do live inferencing. So the way this would work, we would have queries going into SQL, and then we're taking the event data, we're taking the file system data, the object store data, combining all of it. And the end goal is to do anomaly threat detection of malicious activity happening in the SQL layer. But more importantly, we need to correlate what we see happening to a table. That table is mapped, in my example, to say some Parquet files. We need to correlate the query to the files on the file system or the object store that were ultimately affected by that. And by doing that, we now have full end-to-end context that these files were manipulated by this user at the SQL layer, and the action they took was, insert, update, or whatever the user was doing. At the same time, we also need to protect the file system and the object store for activity that is not coming from SQL. And we need to correlate if there's a modification to a Parquet file, did that originate from Trino or not? So we have to draw a big circle around all of the data in the pipeline, all the data sources and all the data manipulation potential, and apply our AI models to protect the data. So demo. So what we're going to show is a simulation. Going to run some scripts that basically simulate the data being manipulated in Trino. There's going to be a bunch of users doing some background activities. That'll just be a script that'll be looping through some automation. Then we're going to take the event listener data and publish that into Kafka. And we're going to then do real-time event listener analysis, looking for deviations. And the way we're going to cause an anomaly is we're going to run another script for a particular user, and it's going to deviate that user's behavior from that background model, and we'll be able to show that detection. Okay, so we're going to go through the demo. It's several different SSH prompts, so I'll walk through what's actually happening here. This session tab is loading up the inferencing engine. You can see the model files are being loaded, the PK files. So here, we're going to be listening for live Kafka data. That would be event listener data coming directly from Trino. And we're going to be comparing it to the model, looking for anomalies. So that's what this tab is here. So we'll play this out a bit more. And then we're going to start up that background traffic where just normal user activity, it's a script that's going to loop through several different user sessions. So we'll get that started. There we go. So there's a bunch of users, user 41, user 76. So some users doing some activity on this script that's sort of simulating background traffic. All of this is generating event listener data. So that's flowing into Kafka. So there's no anomaly because the model was trained on the normal activity in this environment. So all is good. So that anomalous user will go to another session tab, and we will start that session and start a script that will cause modifications and things that are happening to the data in the Trino tables that was not part of the normal activity that we trained on. A second here. So here's that user doing some anomalous behavior, and that's running in parallel to the user activity that was also running in the background. So now this user is doing something that they shouldn't be doing. And we can see here, we now see anomalies coming in, and it's telling us the table that was involved, the user that was involved, and this is some metadata that tells our software what we should do with this. So this is now detecting anomalies for that user. We're also taking the definition of this table, and we're able to turn that into a list of files. And then if that's correlated back to the file system of the object store, we then understand that the anomaly at the SQL layer is what's causing the I/O behavior to the underlying storage where this particular table is stored. And so if this user behavior stops, then the anomaly detection would stop detecting because it's live. This is connected live to the Kafka topic in Trino. So this is giving an indication of a problem. This, of course, would turn into a GUI alert, something that a user could react to and investigate. There'd be a lot more metadata included. This is just the raw output from the inferencing engine. So we would be able to tell how long this persisted for. Did they do this once and then never again? Was this something they persisted over time? Is this something they have done in the past on this particular table? There's a lot of processing that would still occur. This is essentially a raw alert or detection that would be created. The event listener that I mentioned is using what we call the cyber storage framework. This is a standard that Superna is leading with other vendors about what data needs to be in the audit logs in order to be a cyber storage capable auditing platform. Turns out that the Trino environment produced enough metadata that allowed us to map it directly into the cyber storage framework. So that's great news. That means we can incorporate it directly into our anomaly engine. And that's precisely how we were able to build this whole solution in under a month. I'll pause the demo there, and I'm just going to switch back to the slides. And we'll talk about how this fits into the big picture. So if I look at a typical enterprise environment, they're going to have file systems, they're going to have object stores, they're going to have relational databases, and with Trino Starburst deployed, we're going to need to take inputs from all of those environments, run through our training process, then flip over to our inferencing and anomaly detection, and now we can offer enterprises a complete solution regardless of who or what is manipulating the data. So there's the production data. So structured, unstructured, security for data lakes. We can combine this knowledge of SQL and NAS or object and prevent real-time attacks, zero-day attacks, and a complete zero trust capability where we're monitoring users that are trusted and trusted hosts, and we can delineate between a trusted user and an untrusted user and host and apply different anomaly detection depending on which attack vector came in. Then we'll store all of this data for forensics over a long period of time because that's required for compliance with many standards. So we keep all the activity for doing historical behavior analytics. Now, the most important part is, where does this information go? Well, today the average enterprise has 70 different security tools. We are, of course, a new security tool, but we natively integrate with all of the mainstream security vendors. You can see here, CrowdStrike, Palo Alto, Rapid7, SentinelOne, Splunk, ServiceNow. And by doing this, we can present the anomaly detections that are found within Trino or the file system or the object store natively in whichever security tool the customer is using, map all the relevant fields and events so the security team can now execute an incident response automation and take actions to things that are happening to the data that are being detected at this new security layer called cyber storage. So this sort of shows how we put the whole thing together and how this would work inside an enterprise who's looking at using data analytics as a key tool for the machine learning AI environments, and how Superna can actually integrate and combine all of their data sources into a single viewpoint and integrate this into their existing security incident response. So hopefully this enlightened you to the problem statement, and B, the solution to that problem is an offering that's available from Superna. And this is a prototype that I showed around the SQL layer, but the existing file and object solution is a market leading product that's been in the market for over 8 years. So I hope you got a lot out of this session. And I think my LinkedIn profile is on the session. So more than happy to email me questions or follow up. I can be easily reached, and more than happy to discuss this further. So thanks for watching.